also use language, our understanding and knowledge of language to compute, figure out, understand phonemes. This was demonstrated in an experiment done by Rubin and his collaborators. So basically, what they did was they presented two different types of stimuli. They either presented short words, actual real words like sin, bat, and leg, and they also presented short non-words. They made sense phonetically. They sounded like words, but they weren't really words, like jum, bath, and teg. Now, basically, what the subjects were asked to press a button as soon as they heard the phoneme, a proper one of the a phoneme. So, for example, if you were in this study and you were told to press a button when you heard ah, like in bat, so you would sit there and you'd listen to sin, and then when you heard the word bat, you would hit the button. Uh, Similarly, if you heard the word bath, you would hit a button. What they found was that listeners were much quicker at hitting the button when the short words were used as opposed to non-words, which tells us that the short words were processed in a different way, in a shorter way, uh, and the non-words were processed in a cognitively expensive way, something that took a lot more processing, meaning that we do tend, when even when we're looking for specific phonemes, we take the whole word into account, not just the actual sounds, but we do take the whole word into account. Um, Warren did a really interesting experiment where he had listeners listen to a sentence, and one of the phonemes in the sentence was covered by a coughing sound. The task that the folks had was to state where in the sentence the cough occurred. Um, People could not do this. Basically, what happened was they could not correctly identify the position. And they also didn't notice that there was a phoneme missing in the sentence. So what's happening here is that we're not listening to, or what this experiment tells us is that when we're listening to speech, we're not simply processing a chain of phonemes. What we're doing is we're taking a collection of phonemes and looking at it as a whole phrase or sentence or word. So that if there's a little phoneme missing from a word, we're not going to notice it because we're processing at the whole word level, not at the phoneme level. Um, so Miller and Azar did a study where they were looking at the ability of people to repeat or to mimic or to shadow out loud sentences that they heard through headphones. So there were three types of sentences that were given: normal grammatical sentences, weird sentences that were still grammatically correct. They were just strange words that were mixed together. And then just ungrammatical random strings of words. Now, if now think about it. If our ability to perceive words was based only on our ability to parse different phonemes, it shouldn't matter which one of these three you did because you're going to just be repeating phonemes, right? It shouldn't matter if the sentences are normal sentences or just random strings of words. If you're just like parroting back the phonemes, it shouldn't matter. However, it did matter. When people were repeating back these sentences, 89% were accurate with normal sentences, 79% were accurate with the weird sentences that were grammatically correct but had weird words, and all the way down to 50% accurate for ungrammatical word strings. Um, we could make these differences even greater if we put background noise so that there was more challenges to your brain in processing the phrase. And what this tells us is that again, we're not we're not simply perceiving words at the phoneme level. Rather, we are using our knowledge of language, our knowledge of words, our knowledge of sentence structure when we're understanding words. And this is one of the reasons why why it's difficult to get a machine to understand language. Unless that machine has an understanding of language, it's going to have a hard time understanding human spoken words. Um, Here's another thing that we do is perceiving breaks between sequences of words. If you were to look at the uh, auditory output, the spectrographs of somebody speaking their normal language, you wouldn't see clean breaks at the word level or at the sentence level. If you were just looking at this spectrograph of spoken language, you wouldn't be able to tell where words happen and where sentences happen. It would be very difficult. We break down words and sentences based upon our knowledge of language, the knowledge of the knowledge that a listener has about language, and our experience with that language. All of that semantic meaning is used to break down language. So, for example, if you look at this word speech segmentation, there's no way to tell here, how many words are here, where the different, if it's a sentence or word, there's no way to tell that. Again, it's something that we rely on our top-down processing to do. Um, One of the different types of knowledge that we use when we are understanding word structure is transitional probabilities. In any given language, there's a very high probability that one sound will be followed by another sound. Languages vary in the way they have this, but there's always a high probability that one phoneme will be followed by another phoneme in a particular language. One of the things that we do as we're acquiring a language is to learn these transitional probabilities, to learn which sounds normally come after another. And it turns out that babies as young as 8 months old are able to recognize the transitional probabilities. In other words, the way the phoneme patterns happen. Uh, they're able to do this even when they're 8 months old. So this is before they start talking. Before babies start talking, they're already getting knowledge of how the phonemes flow in the language that they're being exposed to. Um, an experiment by Safran and their group did an experiment where they had broken up into several phases. So during the learning phase, babies, little infant babies, heard nonsense words. So words that sounded like they might be real words, but they weren't real words, in 2 minute strings of continuous sound. And these nonsense words that they heard obeyed certain rules of transitional probabilities. In other words, if there was a particular sound, there was a very high probability that it would be followed by another particular sound. Um, the nonsense words were put in random order inside the string, and what they did was they just played these for babies. These words that don't exist, but they contained a fixed set of different transitional probabilities. In other words, a fixed set of one type of sound followed by another type of sound. Um, if infants do use these transitional probabilities, then they should recognize the little units going from one transition to another transition. They should be able to recognize those, even if they occur in a string of babbling, right? They should be able. Okay, so after the babies were exposed to these strings of random nonsense words, we then tested them to see if they would listen, and we tested their attention to listening to either the another test where they heard these whole words again, or we took the components of the words and mixed them up, and only gave them part of these nonsense words that they heard before. Now, if they couldn't tell the difference between the whole word and the nonsense words, they shouldn't pay, they should pay the same amount of attention to both the whole word and the new part word that they were exposed to. However, that didn't happen. What happened was they quit paying attention to the words they had heard before, those fake nonsense words. They quit paying attention to those, and they paid more attention to the new mixtures of these nonsense syllables, which indicates that while they were being exposed to these words, while they were to these fake words, they were learning the transitional probabilities. And then when we gave them new transitional probabilities to listen to, they paid more attention to them because they're new. Babies tend to like to pay attention to new things in their environment. Which tells us that even young infants are learning and acquiring transitional probabilities as they're listening to people speak. And you have to remember this because if you're raising children, one of the big problems that we're having is that people are using texting a lot. They're using texting and their phones, and they're not talking anymore. And you have to remember that babies learn by listening to speech. So if you're raising a baby and you're around a baby, make sure you talk. Don't text too much because that baby is going to be developmentally delayed if you don't talk enough around it. So here's an example of the some of the phrases that were used in this experiments. Bidaku, and in this example, the fake word bidaku, the transitional probability was that the da was always followed by b, which is a transitional probability of 1, right? So b always came before da. Syllables between words, ku from bidaku was not always followed by pa from padoti or tupiro. So that means that the probability of that was only 33%. And when we played these ridiculous words with these probabilities, babies picked up those probabilities. They got exposed to the whole words versus the part words, and like I said, they paid more attention to those part words, meaning that they learned the stimuli, they learned those transitional probabilities, and were more interested in these new transitional probabilities. Um, we also have to take into account different characteristics of a particular speaker. We do take into account age, gender, emotional state, how serious they are. These are a lot of things that we subconsciously take into account as we're processing speech. So Palmieri et al. Had an experiment where they had listeners uh, listen to a sequence of words, and they indicated when a word was new in a sequence of words. Um, they had a much easier time of this if the same speaker was used for all the words. If there was a different speaker with a different voice, like if you went from a male to a female or from a child to an old person, this task was more difficult. So if you think about it, that's kind of weird if we're only listening to sounds and even the semantic meaning, right? It tells us that we're using more than just the sound and the semantic meaning. We're actually encoding a lot of other stuff about the speech that we're listening to. And this model is a very simplistic model that tells us how top-down processing, in other words, our previous knowledge and the meanings of the semantic meanings of the words, interact with the signals that were coming in through our ears to ultimately form our speech perception. This picture tells us that speech perception is much more than simply analyzing the sound that's coming into your ears. It has much to do with the knowledge and meaning and the expectations that we have of a particular language.